my friend and colleague from the University of Strathclyde, Waqquas Bukhsh, who is, as I said, at Strathclyde. His research interests in numerical optimization methods, their application to energy systems. And over to you, Waqquas.
Thank you, Beat. Can you see my screen?
Yes.
Excellent. Hi, everyone. Many thanks for being here. My name is Waqquas Bukhsh, and this is a joint work with two of my colleagues, Callum, MacIver, and Keith Bell. We all are based at the University of Strathclyde. So our paper is called Assessing the Value of Increasing GB Connection. I know that I'm virtually surrounded by very smart people, but just to avoid any confusion, please allow me to clarify that GB stands for Great Britain. Right. So to get some motivation going, I'll start by briefly explaining why we are interested in quantifying the value of GB interconnection and why this is a timely research question. So over the years, there has been a lot of commercial interest in GB interconnection projects. And the interest has been mainly driven by the arbitrage opportunities that existed and still exist between GB and the neighboring countries. Interconnection facilitate renewables and to a certain extent help with the security of supply. And due to these properties, there has been a significant policy push from the European Commission towards increasing interconnection capacity among the member states. Interconnections are big infrastructure investments, so naturally there are many risks and uncertainties involved in such projects. In Great Britain, we have 5 operational HVDC links with the total capacity of 5 gigawatt. The figure you see on this slide is a cutout from the European scale 10-year network development plan. And if you look at the full figure, your eye will be immediately drawn to the area around Great Britain, as it is quite a busy place when it comes to the proposed interconnection options. There is approximately 13 gigawatt of interconnection capacity in the pipeline and 3 projects that are under construction, 2 to France and 1 to Norway. So as I said on the previous slide, the growing GB interconnection project pipeline can be seen as a natural commercial response to changing market and regulatory environment. However, the impact of this increase in the interconnection capacity in terms of price and carbon emissions is still uncertain. And that's the main research question that we are trying to take up in this paper. The research is part of the wider project that looked into various interconnection investment questions, including post-Brexit outcomes, and also the stability questions related to the increasing penetration of non-synchronous power. So this paper provides a modeling framework for quantification of the value of the additional interconnection capacity. And for that, we'll be using 2 metrics, the marginal price of electricity and the changes in the carbon emissions. So we have developed a European scale electricity dispatch model. This model is implemented in a tool called Antares, which is developed by the French electricity transmission system operator, RTE. The spatial scale of the European model is 35 nodes, which are connected by 98 links. Each node represents a European country with a couple of exceptions. The temporal horizon is 1 year with an hourly resolution. With the modeling framework, 1 year is converted into sub-problems of 1 week on which generation is dispatched. We model the thermal generation down to the unit level. And along with it, we model all the temporal constraints like ramp rates, minimum up and down times. So in the interest of time, I'm not going to delve into the details of modeling. That's something you can read in the paper. I'll just like to highlight a couple of assumptions that are used in the modeling. First is the market clears as a fully coupled and assuming perfect competition among the participants. Secondly, the model dispatches generation with perfect foresight of demand and renewable generation availability. So the data we have used in the paper came from the 2018 10-year network development plan of NSOE. In this paper, we are considering scenarios for the years 2020 and 2025. The wind and solar time series are projected based on the historic data available from the Renewable Ninja. And for each European country, we model the hydro generation based on the historic realized data, which we obtained from the NSOE transparency platform. So we have constructed and tested several interconnection scenarios for the years 2020 and 2025. For the year 2025, we have 5 scenarios modeling different arrangements of the 3 projects which are under construction. So first scenario is the base with the 5 gigawatt of existing capacity. The next scenario models the commissioning of ElecLink, which is a 1 gigawatt link to France. This link is in advanced stages of construction, and we believe that it will be the next one to connect. Then the scenario tree branches out between AFA2 and AFA2, which is a gigawatt link to France, and NSL, which is a 1.4 gigawatt link to Norway. So scenario 3 and 4 are essentially modeling 2 possibilities between timing of commissioning of AFA2 NSL. So finally, scenario 5 is all 3 links in operation. That takes the total GB interconnection capacity to 8.4 gigawatt. Similarly, for the year 2025, we start with a base case of 8.4 gigawatt. And there are 8 different scenarios that model various combinations of 4 interconnection projects, taking the total GB interconnection capacity to up to 13.1 gigawatt. So these scenarios were constructed in consultation with the stakeholders, and there is a thought process behind each scenario trajectory, which you see on this slide. Here is a figure that presents the impact of the 5 GB interconnection scenarios on its marginal price. You can see from the figure that the marginal price is decreasing, and the solid line you see is a regression line. So we note that the decreasing marginal prices as the GB interconnection capacity increases. This is because Britain is connecting to France and Norway, which are systems with lower marginal prices. The gradient of the regression line is minus 0.5, which represents expected euros per megawatt hour reduction for a gigawatt increase in capacity. So which means if GB interconnection capacity were to increase from existing 5 gigawatt to 8.4 gigawatt with the modeled scenarios, the annual average margin price is expected to reduce by 2 euros per megawatt hour. This slide shows the impact on carbon emissions of the increasing GB interconnection. The bar chart you see is the incremental impact on carbon emissions. So moving from scenario 1 to 2 significantly reduces GB carbon emissions, and it also reduces total European emissions. We notice the same when we move from scenario 2 to 3. The transition from scenario 2 to 4 is interesting. The GB carbon emissions reduce significantly in this case, but there is an increase in the total European emissions. The scenario represents GB connection to Norway via 1.4 gigawatt link. The European emissions increase because GB gas is being displaced by more carbon intensive but cheaper generation in the mainland Europe. These figure represents average absolute difference on the x-axis and the average utilization of the links on the y-axis for the 5 scenarios in 2025. The utilization and average price difference decrease with increasing capacity. So as we move from left to right on the graphs, we notice that the dots are moving towards the origin. In these scenarios, we have 2 links to France with 2 gigawatt of capacity. That reduces the average price difference between Britain and French markets by 4 euros per megawatt hour. But as the results, from the results, you can see the reduction in utilization is less than 2%. GB is not connected to Norway in the first three scenarios. So you can see the utilization of 0 in the first three figures, and the price difference of approximately 11 euros per megawatt hour. When GB connects to Norway in the fourth scenario, we notice the price difference reducing by 2 euros between GB and Norway. So in this paper, we have considered two price scenarios for the year 2025, gas before coal in the merit order and coal before gas. So in the interest of time, I'm only going to talk about gas before coal price scenario for the year 2025. So this slide shows the result for that particular scenario. We have also considered two possibilities. Apologies. So we have also considered two possibilities for the carbon price support. Carbon price support is a UK-specific additional carbon fee on carbon emitting generation within UK. So the graph without carbon price support shows the GB margin prices are increasing slightly. This is because the prices in GB and Europe have equalized in 2025 in that particular scenario. And GB is importing less and have also started to export in certain time periods. The impact with carbon price support varies depending on the connecting market. And we see the regression line is flat because the interconnectors are canceling each other's impact. Increasing interconnection capacity to France still decreases GB prices. On the other hand, connecting to Ireland, we are seeing increasing GB margin prices. So this graph shows the impact of increasing interconnection on carbon emissions. Without the carbon price support, the emissions in GB increase due to the increased exports and decreased imports. The GB gas is displacing more carbon intensive generation in mainland Europe. Because remember, we are considering this scenario gas before coal. With carbon price support, the impact on carbon emissions depend on the connecting market. The general trend here is that the increasing GB interconnection capacity is resulting in overall reduction of carbon prices, carbon emissions. So the last thing which I would briefly like to mention is the importance of modeling line losses in such studies. Our simulations have shown that modeling of losses is very important, and failing to model losses may result in loop flows or overestimation of interconnection utilization or underestimation of the marginal prices. The graph demonstrates the importance of modeling losses with an example of a link between Britain and Norway, where we see overestimation of utilization by 8%, underestimation of GB margin price by 2%. And these errors have implications in investment appraisal analysis. So finally, to sum up, there are a few takeaway messages from this paper. Firstly, the three interconnection projects that are under construction, 2 to France and 1 to Norway, will have a positive impact on the GB margin prices while having a minimal impact on the utilization of existing links. But as the GB and mainland European generation exchanges and more renewables come into the system, and with the lifting of carbon price support in UK, GB prices are expected to come closer to the neighboring countries. And at that stage, new interconnection projects will start to eat into the utilization of existing interconnection projects. Secondly, in terms of carbon emissions, we have noticed overall European carbon reduction in the case of gas before coal and without the UK carbon price support. With the UK carbon price support, we noticed significant drop in the GB carbon emissions, but that reduction may come at a cost of overall increase in the European carbon emissions. So finally, many thanks to Callum and Keith for their support with this paper. We are grateful to EPSRC for the funding that we received for this paper, for this research project. And with that, I'll pause and thank you very much for your attention. And I'm happy to take any questions that you may have.
Yeah, okay, thanks very much, Waqquas. And yeah, I don't know if you can see the Q&A yourself, but we have a question from Robin Smith, your results are presented in terms of per megawatt capacity addition. So how are the power transfer capability constraints accounted for in the simulation? Typically, a megawatt intertie increase need not result in a megawatt transfer capability increase.
Right. Yeah, so the scenario constructed were based on the megawatt capacity. So, so going from one scenario to another, I mean, it was not an incremental increase in the megawatt capacity, if I'm getting the question right.
Yeah, or maybe, I mean, I don't know, maybe in the question, I'm kind of wondering whether, you know, if it's within an AC network, just having the thermal capacity, for example, of a particular line doesn't necessarily mean that you can increase the total transfer across a boundary, you know, which maybe has multiple lines, you know, because of constraints within the network. Doesn't mean you're going to get all of that extra benefit because there's an interaction. But actually, in this case, there are DC links, so they're very controllable. And we haven't modeled the within network constraints, have we?
That's true, and that's a fair point. But we need to remember that we are doing it in a market setting, and at least in GB, the market doesn't care about the transmission network. I mean, obviously there are costs associated with, I mean, at the end, we need to respect the physical laws of the network, but how the market clears that doesn't take into account the actual physics of the network.
Yeah, so actually in the work, I know I happen to know this being involved in the work, but there was another stage of trying to calculate the redispatch cost as a consequence of the within network constraints. So a bit like what, yeah, I think it was Pierre was talking about. You know, there's a cost of redispatch to kind of, yeah, correct what the wholesale market, which only has a very simple kind of representation of the capacity of the network, would have done.
Sure, yeah. So there are subsequent costs on a market solution, which comes in different time horizons, so in a balancing stage or on a real-time basis.
Yeah, so I hope that answers Robin's question, more or less. There's another one that's come in. Are the benefits symmetrical between Norway and GB, for example? Yeah, I mean, the modelling does calculate what happens to the average price in Norway. Didn't present it in the presentation. Can you remember what was happening there as the price was coming down in GB? By how much was it going up in Norway?
So just on the top of my head, the impact was not symmetrical. There was more price reduction in GB as compared to Norway. So it's and as we saw, the carbon emissions in that case gone up. So the generation in the peripheral countries, they were using Norway as a route in the model to ship power.
Yeah, because it's a curious thing. An interconnection to a hydro-dominated network results in increased carbon emissions.
True. Yeah.
It's like, so actually what seems to be going on is a kind of a transfer through Norway, or perhaps different kind of patterns of utilization of the hydro resource.
Yes, yeah. So in that case, we saw increased more carbon intensive generation, for example, in Poland and in Germany with the SL link.
Yeah, so so I hope that answers Adonis's question, but actually you can sort of start to see that there's a lot of sort of complex stuff going on, you know, within the 8,760 hours of a kind of a year that's being simulated. Okay, so I think thanks very much, Waqquas. Again, I think in the interest of time, we'll move on from there. So yeah, thanks a lot.